Good evening, everybody. Thank you for introduction. I would like to share with you some of our recent results, which were obtained in collaboration between our ETMO University in St. Petersburg and two French organizations at once. The first organization is the Institut Fresnel in Marseille, and the second one is the CEA Neurospin in Paris. And we will talk about how is it possible to construct a completely new design of a radio frequency coil for scanning of small animals, which is cheaper than the state of art and gives better performance in terms of homogeneity of the field and penetration. So we will start with a small overview. What is the capabilities of preclinical imaging, and what are the conventional designs of radio frequency coils which are used for scanning small animals. After that, we will discuss our idea, which uses the effect of hybridization of agent modes in resonant wire structures. After that, we will consider our particular new geometry of the antenna, its simulation results, the results of measurements in the laboratory, and the results of the testing of this radio frequency coil in a real preclinical system Bruker at 7 Tesla. And after that, we will come to our conclusion. So what we know about preclinical MRI? Due to the great achievements in superconductive magnets, it became possible to create very high static fields in a small region of interest. So it is possible to have a very good resolution when scanning small biological objects. And these achievements made possible the following advanced methods in MRI, such as functional imaging with or without contrast, multi-nuclear spectroscopy for investigation of metabolic cycles in tissues, ultrafast and high-resolution anatomical images, which can give you the resolution up to 200 microns for the scan time of 1 hour only. So, for example, on this image you can see how good can be the anatomical images, the hydrogen images of a brain of a mouse, which is very small, when we use a preclinical 7 Tesla scanner. Or if we want to scan not only hydrogen but several nuclei at once, we can use dual frequency MRI, and we can superimpose different images, which is very useful in different biomedical applications. Yeah. So, of course, this kind of preclinical imaging requires radio frequency coils, because radio frequency coils are required in every MRI machine in the world. And I would say that in case of preclinical MRI, these coils are very specific. The first reason for that is that the environment is very specific. These coils, radio frequency coils, they must operate inside a very narrow metal tube, which is the RF shield of the tunnel of the machine. Yeah, and another issue is that these coils must be very small, because normally the size of the radio frequency coil must be comparable to the size of the region of interest. In this case, the region of interest is the head of a mouse. You can imagine how small is this coil. So this is a very electrically small antenna. Also here, this is the leg of a rat. You can see how small can be the radio frequency coil. Also, because this environment is very specific and these are very small coils, they are very sensitive to the subject and very sensitive to the environment. And finally, in order to use these coils, you need to tune and match the coil every time before you want to make a scan. So, for example, if you move a little bit the antenna inside the machine, or you replace one subject with another, you need to retune the coil again. For this purpose, engineers usually use, and not only engineers, actually it is made by scientists or doctors, I don't know. These coils are usually tuned to the Larmor resonant frequency by means of lumped variable capacitors. And these are depicted on the slides here. So this is the capacitors. And in order to tune and match the antenna, the capacitors must be tuned by means of special very long fixtures which you need to rotate every time before the scan. And here there are some problems. These capacitors are extremely expensive because they need to be non-magnetic, they need to be high power, and they need to be variable. Also, another problem is that a lot of losses inside this coil is due to these capacitors. And therefore, the presence of these losses limits the capability of radio frequency coils and limits the reachable signal-to-noise ratio. So when you would like to work at two frequencies simultaneously to scan two nuclei, it is even a bigger problem because to tune and match a radio frequency coil at two frequencies simultaneously and independently, you need to have at least 4 variable capacitors in your schematic. To do it more comfortable, you have to use even larger amount of capacitors. And if we recall ourselves that the price of each capacitor is around $300, then the price of the wall antenna can be as large as $1,000 or $2,000, which is extremely expensive. It would be great if we could avoid using capacitors like this, yeah, and if we could improve the signal-to-noise ratio. In our idea, we use the effect of hybridization of agent modes in resonant wire structures. If you take a wire with the resonant length, which is close to half wavelength, it can be considered as a resonator with its resonant frequency. For example, it can be tuned to 300 MHz, which is the Larmor frequency of hydrogen at 7 Tesla. Then it has one resonance only. And we can, in principle, we can use it in MRI. And there are some studies where dipole antennas are used instead of loops at 7 Tesla. This is now a very popular topic. And if we take two dipoles, due to the interaction between them, we can use two agent modes. This is the effect of hybridization. These agent modes have their resonant frequencies at slightly different frequencies. Yeah? If we have 4 resonators, we have 4 agent modes. And in principle, we can make a coil for 4 frequencies out of this design, which was, this kind of coil for 7 Tesla for preclinical imaging was done by our colleagues from France earlier this year. And in our case, we would like to scan at 2 frequencies simultaneously. First frequency is the frequency of proton. At 7 Tesla, it's around 300 megahertz, and another frequency is 282. It's the frequency of fluorine at 7 Tesla. We take the structure of several parallel wires, and since the size inside the bore is limited, we need to make these wires very small. They cannot be half wavelengths. For this purpose, we load them to this structure, periodic structure of metal square patches, which behave as capacity. And with these patches, this can be resonating at 300 megahertz approximately, with the size of approximately 5 or 6 centimeters, which you can place inside the bore of 9 centimeters in diameter. The preclinical bore, for example, a Bruker machine. So there is no problem. And in this system, there are multiple wires, so there are multiple resonances. There are multiple agent modes. And in principle, you can excite each of these agent modes. And the problem is that these agent modes have different field distributions. Yeah, but for us, it would be more convenient to use the most homogeneous one, which is the most having the lowest possible frequency. So we finally use 4 systems of wires. One system of wires is the system of longitudinal long wires in parallel to the axis of the scanner, and another system is perpendicular to the axis of B0. In each of these 2 systems of wires, we can excite the lowest resonant mode with very good penetration and very good homogeneity. And we excite these agent modes by means of a small loop antenna on top. And this is our subject. This structure is absolutely self-resonant. So in order to tune it to the resonance, we don't need any capacitors. We can tune it to 2 desired frequencies independently just by modification of the length of these wires and their mutual position. And that's all. So we can avoid using these expensive capacitors. In order to prove this, we run a full-wave numerical simulation in CST Microwave Studio, where we can calculate the return loss, so the reflection coefficient in the cable feeding this antenna, which shows us that really we can tune to these two particular frequencies of fluorine and for proton. And this is the field distribution at these frequencies. We can see that inside our subject, the field is quite homogeneous. So this is the photo of the PCB boards which are used for this sample, for this antenna, for this radio frequency coil for two frequencies. So this is the long wires. They are printed on the substrate, and this below there are the short wires loaded with system of patches, also realized as PCB boards. And this is the feeding loop, which is non-resonant itself. And by means of vector network analyzer, we can check that really we have two resonances, and our impedance matching is very good. So all the energy applied to this antenna goes to the subject at two desired frequencies. And we can tune these frequencies, and we can match the impedance of the antenna. And after that, our antenna is ready for testing, and we put it to the preclinical MRI 7 Tesla Bruker thermoscan, and obtained several images for two nuclei, fluorine 19 and proton 1, for two different pulse sequences. It's T1 weights gradient echo and T2 weights spin echo. And we can see that the level of the signal to noise, we use the phantom, which contained a mixture of 3-fluorethanol and water to have this nuclei inside. And what we can see is that we can really reach the signal to noise ratio up to 20 or 30 with this antenna, which is comparable to the performance of conventional coils, which are tuned and matched with capacitors. But here we can avoid these capacitors and make it much cheaper. It's one order. We win one order in price of this antenna. And to make a conclusion, I would say that using such systems, it is possible to construct much cheaper designs of preclinical antennas, preclinical RF coils, and the specific of these periodic structures allows us to have much more degrees of freedom to control the near-field distributions, because we can excite and use multiple agent modes inside the structure. And despite that these small animals are really small, this problem is very important, because it can give new possibilities for biomedical studies all over the world. Okay, thank you very much.
Great questions.
Правильно ли я понял, что ваши катушки должны быть ортогональные друг другу?
Вы имеете в виду две системы проводов, да? Вот
да, две системы проводов.
Они должны быть ортогональными по той причине, что в этом случае они имеют наименьшую зависимость. То есть мы можем...
Ну да, индуктивная связь наименьшая.
Да,
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 так, да.
верно.
Спасибо.
Thank you for this nice idea. My question is the following. You are using the system for the program machine. It means you have a relatively small internal diameter. What about as an application of these ideas to a real imaging system like 9 Tesla machine? And the second part of the question, I understand that this is valid in a certain frequency range. What about to increase the frequency to go to a very high field?
Mm-hmm. So this was done at 7 Tesla with the frequencies close to 300 megahertz. And the tunnel was really small. It was 9 centimeters only. In principle, the same antenna can be used for body imaging for human, for example, at 7 Tesla with a large bore. So the size of the bore doesn't matter for the principle of this antenna. You can still use it. And concerning even higher frequencies, for example, 9 Tesla or more, it's also possible to do. So here there was a problem that these wires should be very small. If the frequency is higher, then even this is not a problem already. So it is even easier to use this principle at higher frequencies. So I think it's possible, yeah. So we tried to use it at 17 Tesla for microscopy.
Yes.
but this work is not finished yet because you need to make it very, very precise in order to excite these resonant modes. So there are some technical challenges, but we are working on this currently.
Okay. Any more questions?
Okay, I have one.
Yes.
Thank you for the very interesting presentation. I think you guys in ITMO are going to redesign the MRI, and you're going to redesign it to look like a barbecue party. Okay, my question is, why do you need the square patches?
The square patches, they allow us to make the resonant wires shorter. For example, these long wires must be approximately half wavelength.
Okay, how do they work? I get that. How do they work? How do they allow us to make them shorter?
Because you can imagine that this structure is composed of two-wire transmission lines. Yeah. For example, these two wires can be a transmission line,
Yeah.
and the wave can travel along the wires. If you want to make it shorter, then you need to mimic somehow the properties of this termination. So you can load it with the rest of the line, or you can load it at this point with something else, which will have the same properties. And from the theory of transmission lines, it follows that here you need to put the capacitor, and you will not change the field here on internal part, and you can just throw away this ends if you have the capacitor.
Okay, I get it. Thank you. How about the loop? Why do we need it?
The loop, we took the cable, ended with the loop. The loop was just to excite one resonant mode here and one resonant mode at the long wires. It's just for excitation. So we need some coupling, yeah, with our structure. And by the tuning of this coupling, it was tuned by the distance between the loop and one set of wires, between the loop and the second set of wires. We can obtain impedance matching. So we can match the impedance to 50 ohm.
Okay, thank you.
Excuse me, but I should stop the discussion. Thank you very much.
Thank you.